Hello everyone, welcome to a new video on group theory. Today we're going to prove that the order of an element is the same as the order of its inverse. This is a very easy proof, even if it requires some extra thinking, some cure of details, but you'll see at the end that this proof brings some very pretty and interesting logic insight. So let's start with few preliminaries. Remember that if we have a group G and an element A of the group, then the property, so if we have, and also we have an integer n, then a to the n inverse is equal to a to the negative n, which is equal to a inverse to the power n. So this property holds for every element of every group, as long as n is an integer and you operate only one element. Remember that even with two elements, if we have a, b, and b is another element of the group, ab to the power n is already not a to the n, b to the n. Remember, this is ab, 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 ab. I mean, it's not necessarily. So it might be true, but not all the time. So this property holds for groups, which actually is not quite intuitive. All right, said that, we're going to deal with orders. So let's recall what do we mean by the order of an element. So the order of A, so A be an element of the group, is the smallest integer, call it k, smallest integer k, such that a to the power k is equal to the identity. This is the key of the definition and is obviously the key of our proof. It's going to be the key of our proof. What does this mean? It means that this statement is not true. It might be true for another integer if we call it j. So it might be that a to the power j is also a operated with itself j times will also generate the identity. But if these two are both true, then j must be greater than k, or they're equal. Okay, so let's start with the proof. Let's reclaim for clarity. So let's rewrite our claim. So we have A be an element of the group and G is a group. Then the order of A is equal to the order of A inverse. All right. Now we're ready to start our proof. Let's pick two integers. Call it n and m be integers, and obviously we're dealing with orders. So let m and let n be the order of A. Okay, n is the order of A, and let m be the order of A inverse, with n not equal m. Okay, so basically what are we doing? We're going with a proof by contradiction. So out of these elements that we have, what can we do? So since the order of A is n, then we know that, so notice that A to the power n is equal E. All right, so what this is going to bring? What happens if we take the inverse of this? We have the A to the power n inverse remember the property we explored before. This is equal to a to the negative n, which is equal to a inverse to the power n. On the other side, if this is true, then this brings also that a to the power n inverse is equal to the identity inverse, which is equal still to the identity. So this, if we enchained these two lines, we get that this is also equal to the identity. And this is our first result. Now, when I first saw this, I wasn't really quite satisfied. This proof is, if it's not taken in details, is not really satisfying. But what is this saying? It's saying that if I take the inverse of a and raise it to the power n, I get the inverse. Okay, but by definition of order, we know that a inverse to the power m is also equal to the identity. We also know by definition of order that m is the smallest integer that makes this true, right? So what does this mean? It means that either n is equal to m, so is the order of a, or n must be necessarily greater than m. So let's write this down. We get the let's put it this way. M must be less or equal than n, since m is the order of a inverse. Okay, now what else do we know? We know that the order of a inverse is m, so we get the order of a inverse, or a inverse to the power m is equal to the identity, right? Let's take the inverse again. We have the inverse to the power m inverse is equal to a inverse to the power negative m, which is equal to a to the power m, right? Now, still, like before, if we take the inverse of this, then it's like taking the inverse of the identity, which is still equal to the identity. So this is equal to the identity. For an analogous argument, remember that the order of a was n, so a to the n equal the identity, and n was the order of a, so it was the smallest integer that makes this true. So what it means that n must be either they're the same, right? So they both are the smallest possible integer, so they're the order, or n must be necessarily be less than m. So we have the n is less than m, okay? Less or equal than m, okay? Now, let's compare these two results. We have the m is less than or equal than n is less than or equal than m. This is true if and only if n is equal to m. And the proof is concluded, right? However, this comes a really nice part of this proof. Why? Remember that we started the proof with a contradiction, all right? So our statement that n was equal to m was a contradiction. So what are we expecting when we do a proof by contradiction? We expect that something bad happens, right? We do not expect a result. We're not seeking for truth, right? We are expecting a negation, a contradiction of our statement, or something bad. So if we think about it, this is our final result, okay? But if by using another kind of, if the same procedure or another procedure, it doesn't really matter, brought the result that n is not an integer, all right, or m is not an integer, wouldn't be the proof. Would the proof be the same? Well, yes, because we started by saying that n is an integer, and at the end we had that n is not an integer, which is a contradiction, which our statement would have been proven anyways, because something bad happened. Or doesn't, how about at the end of this proof we found that 3 equals 7, right? Wrong. There was something bad, something that contradicted our integer properties. Okay, so what did this do? n equal m equal n contradicted our assumption. Okay, since it contradicted our assumption, whatever the result was, our assumption has been contradicted. Since we're dealing with non-ambiguous statements in mathematics, then this must be false. So n must be equal m, all right? But not because it's written there, not because of this. It's kind of, this is a double true proof. Okay, so it's true because of this, and it's true because this contradicts our statement. Okay, I repeat, if we found this result, it would have been the same, but we wouldn't conclude that 3 equals 7. We would conclude that this is wrong. Out of our assumption, this is wrong. This would be wrong anyway. In this case, okay, we wouldn't conclude that, oh, so then n is not an integer. No, we would have concluded that since this contradicts our assumption, then our assumption is false. So since this was our assumption, then this was true. All right. So again, this is not the result. It's funny that this is actually the result, but the result comes from the contradiction of our assumption. This is the element that contradicts our assumption, not the result. But anyways, this is also at the end we can conclude from here, since our assumption has been contradicted, that this is the result. And since n equal m, then the order of an element is equal to the order of its inverse. Okay, I hope you enjoyed. I hope I didn't confuse you. Thank you for watching. I'll see you in the next video.